Okay, good. Well, welcome to the second part of this course. Okay. All right. So, okay. So in the second part, we are going to be talking about probability. Okay. So. And today, in particular, we'll talk about counting. But before we do that, let me say a little bit about probability. Okay, can we settle down here? By the way, one thing I said a little while ago is, the policy on tech in the classroom. So let's update it. Okay, so I'm not sure how many people here actually use a laptop for notes, but at least there's no reason you should have a cell phone out in the class. So no cell phones at all, and we'll try to see how many people actually use laptops for taking notes. But if that's not really what you're doing, then we'll go to a no tech policy altogether. Okay. So now as we said in the there was a. This is really a great chance for you to, since we are starting from scratch, to really, if you're not already experiencing the course in the right form, it should be much easier to follow the course if you're up to date with it. Right, then you're not always trying to catch up, and then these concepts don't make so much sense, and so on. It's much easier if you stay up to date. Okay, so this is your chance to stay up to date and not let go of that. Okay, so let's try to do that. I'll try to make sure that the basics of probability, which is counting and probability spaces, which is what we'll talk about today and next week. This is what you should really make sure you understand well, and then you'll be able to keep up with what's happening. Okay, so let's talk a little bit about probability theory, which I assume most of you know something about from before, but we'll go over the basics and we'll say, and then I'll try to tell you why, if you want to, in order to study probability, we really have to study how to count. Why is that so important? So let's do an example. Let's do an example of flipping a fair coin 300 times. Okay, so each time it comes up either heads or tails. And now, of course, we expect there to be 150 heads. Right? That's what we expect. But how close would we be to 150? Okay? So here are the numbers. So if you were to ask, what's the chance that you're in the interval 150 minus 17 to 150 plus 17? Okay? What's the chance that you're not in this interval? Right? So outside of this. It turns out that chance is quite small. It's 1 over 22. Okay, roughly. Okay, that's about. So it's pretty closely concentrated around 150. But now you could ask, well, what about if you make this interval a little bit larger, so 26? What's the chance we are outside of this interval? Right, that we are not within 26 of where we expect to be. And this chance gets much smaller, 103.70, roughly. Okay, so it's dropping quite fast. And now if you go up to something like 150 minus 34 to 150 plus 34. Okay, the chance is already something like 1 over 16,000. Okay? So already for a fairly small number of coin flips, 300 coin flips, somehow the chances that you don't get very close to 150 heads, is quite small. It goes down quite rapidly. Okay, and this is for 300. As you make 300 larger, as you make the number of coin flips larger, the concentration around the mean gets more and more dramatic. Okay? So now, why is this the case? Okay? Well, let's see if we can understand that a little bit. And somehow this example is going to tell us a lot about why probability behaves the way it does. So we have 300 coin flips. Now you can ask, how many possible outcomes are there? Okay, well, you could get all tails or all heads, or you could get heads, tails, etc. How many possible outcomes are there? Well, there are 2 outcomes for each coin flip. There are 300 of them, so there are 2 to the 300 possible outcomes. And this is about 2 times 10 to the 90. Okay? Now, how big is 2 times 10 to the 90? Well, here's something that should give you a hint. The standard sort of estimate for the number of particles in the visible universe is about 10 to the 80. Okay? So this extremely modest experiment in probability already, the number of possible outcomes of this experiment is that large, right? Okay, so now you could ask, what about, what should I expect to get as an outcome? Instead of asking, what's the chance that I got close to 150 heads? Suppose I said, what's the chance that I got all heads? Right, so what's the chance of getting 300 heads? Well, it's only one outcome out of 2 to the 300. Right? So the chance of seeing this is incredibly small. Right? It's unimaginably small. It's like saying, we are going to pick at random one of the elementary particles in the universe, and the chance that we find a particular one, right? That's much, much larger than the chance that we'd get all heads here. Okay? That's a ridiculous number. Okay, so what this is telling us is, well, there are, it's sort of showing us that there's something very interesting that happens with probability theory. Well, first, that when you do a probabilistic experiment, like flip a coin 300 times, one of the phenomena that happens is that you have this unimaginably large number of outcomes, possible outcomes. Okay, so the number of possible outcomes speaking very conservatively, is astronomical. Right? Because astronomical doesn't even begin to describe it. It's much bigger than that. Okay? The second thing that happens is, because the number of outcomes is so large, suddenly we get a lot of stability. You'd imagine that if you flip coins, you should get, you should see completely random outcomes. Random outcomes means unstable, right? Next time you do something, you should get a completely different outcome. Yes, that's true. But it depends upon what you're looking for. If you're looking to ask exactly which coins came up heads and which came up tails, yes, it's going to change every time. If you're going to ask what percentage of the coins came up heads, that's going to be incredibly stable. Right? So you get the other thing that comes out of this, because there are so many outcomes, if you ask a question like, what's the percentage of heads, you get incredible stability. Right? If you ask the right questions. Okay? And this incredible stability is, this is what makes the world the way it is, right? Because, of course, if you look at the world around you at a suitably small scale, then it's very probabilistic, right? They're atoms, molecules, right? And the atoms are jiggling around, and they are incredibly unstable, right? Well, if you want to look even further, deeper down, then your elementary particles are described by quantum mechanics, which is inherently probabilistic, right? So I mean, there it's all chance. There's not even, things don't even exist in the way that we think of them normally, right? But then the stability we get of the world around us, it emerges because of this. Because the number of possibilities is so large. And then you ask the question, what's the chance that this table is here? Well, there are many more than 2 to the 300 possibilities there. But of those possibilities, because now there are more than 300 coin flips that are being done, right? There are actually a very large number of coin flips that are happening. And of those, if you ask, what's the outcome which makes the table end up here? Well, almost all of them, right? It's practically impossible for the table not to be here, right? Just by chance, just because of the jiggling of the atoms. Okay, so probability theory is extremely powerful. It's extremely fundamental, okay? But like many powerful fundamental things, it started as a game, right? That's what those are the most powerful things. And in fact, how did probability theory start? Well, it started with, our basic instincts, gambling. Right? Those are the origins of probability theory. And then, it started with gambling, it started as a pastime, it was a game, right? And then over time, it became one of the most important theories we have. And I said, as I said, it's completely fundamental to understanding the world around us in terms of physics, but it's also completely fundamental to computer science, so to machine learning. So it shows up in physics, it shows up in machine learning, in AI, it shows up in computer security. Okay. If you want to deal with massive data, you have no alternative but to use probability, to use randomized techniques there. Okay, so this is an incredibly important subject. It's an incredibly important, incredibly powerful, very practical subject. Okay, but it's also a subject you can study at many different levels. So some of the concepts are best understood in terms of games and gambling. And then, after a little while, we'll start studying actually more computer science-like applications of it. Okay, so now, if you want to study probability, one of the most important things basic things we have to study is these large numbers. Okay? Because they are what drive probability. So how do you calculate these large numbers? Okay, so this is going to be something that we're going to talk about today. And this is one of the most, basic things that you have to do with probability. So if you want to compute a probability, you have to talk about, well, if you want to compute what's the probability that you get exactly 150 heads? What you have to do is you have to say, well, how many ways are there if I'm tossing a coin 300 times of getting a sequence which has exactly 150 heads? Right? So if you were saying, what's the chance of getting 300 heads? How many ways are there of tossing a coin where I get exactly 300 heads? And the answer is exactly 1, right? That's the only sequence there is. What's the total number of possible sequences you can get? Well, it's 2 to the power of 300. So the probability that you will get this outcome is 1 divided by 2 to the 300. What about the chance that you get 150 heads? Well, you have to count the number of sequences you get, which have exactly 150 heads and exactly 150 tails. Okay? You count that number and you divide that number by 2 to the 300, and that's the probability. So if you want to compute probabilities, you've got to learn how to count. Okay? And so that's what today's lecture is about. It's learning how to count. Okay, so now what's going to help us do this counting is that we have certain rules of counting. Okay? And one of these is the multiplication rule, which we've, in a simple form, we've already appealed to it right here, right? Because what we're saying is there are 2 outcomes to each coin flip. It's either heads or tails. And now we have 300 of these. So how many possible outcomes are there when you toss the coin 300 times? And what we're saying is, well, there are 2 outcomes of each. Each outcome doesn't affect the next one. You can have any of heads or tails for the first one, any of heads or tails for the second one. And no matter what you got the first time, you can do either heads or tails the next time, and so on and so on. And therefore, you have 2 times 2 times 2, right? So you have 2 times 2 times 2 times 2, 300 times. Just to break this down further, what we are saying is, no matter what the outcome is on the remaining 299 tosses, you can either start with the heads or you can start with the tails. Right? So if you count the number of coin tosses you have, possible tosses you have of 299 tosses, then you multiply that by 2 to get 300. Right? Okay. Okay, here's another example of this. You're rolling a six-sided, you're rolling six-sided dice. How many possible outcomes are there? Well, so suppose you have 2 dice. Right? The number of possible outcomes for each one is 6, and so you have 6 times 6 equal to 36 possibilities. Right? So you get either 1 and 1, 1 and 2, etc., etc. It's all possible. 36 sextuples. Okay. If you have 3 dice, would be 6 times 6 times 6, and so on. Okay, but now let's do a slightly more interesting example. Again, hopefully it's an example you've already seen, but we are going to work through these and do it systematically, so we get to a point where we'll get to things that you've not seen. But they're going to be building off of these, right? Okay, so let's look at the case of permutations. So you have a deck of cards. So you have 52 cards, and you want to know, how many possible, if you shuffle the deck, how many possible ways are there of arranging the cards in the deck? Right? How many ways to order the cards? Okay. So now, again, we can try to use the multiplication rule. And we'd say, well, look, there are 52 ways of picking the first card. Okay, so we have the entire deck. We want to arrange it. There are 52 ways of picking the first card. Okay. All right. So is it true that we can use the same reasoning we did up there to say how many ways are there of picking the second one, and so on? So can we say, for example, no matter how we arrange the rest of the deck, X, there are still 52 ways of picking this card? No, right? Because once I tell you what the rest of the deck looks like, I've uniquely determined this card. Right? So it's going to be a different way of reasoning about it. In fact, let's approach it the other way. Suppose I tell you which card I picked as the first card. So there were 52 ways of picking the first card. So I might have picked the ace of hearts here. Okay? And now, how many ways are there of picking the second card? Well, there are 51 ways, but there are all those ways which do not include the ace of hearts. Right? So the ways of picking the second card depend upon which one I picked here. Right? If instead what I had picked was the ace of diamonds as the first card, then which 51 cards I have available here changes. But the point is that no matter which card I pick here, there's going to be 51 cards that are eligible to be picked for the second position. So which cards are eligible is going to depend upon what I picked here. But the number is independent. Right? Okay, so let's say I pick some card here. Now, which cards are eligible here? Well, it's everything except these two. And so, again, the set of cards that's eligible the next time depends upon what you already picked, but the number is independent. Okay? So now the multiplication rule can actually be modified to take care of this condition. And what it says is, as long as the number of choices is independent of what you've picked before, then you can go ahead and multiply these numbers. Okay, so the number of possible orderings of these cards is going to be 52 times 51 times 50 times so on times 3 times 2 times 1. Okay. In general, if these were not 52 cards but n objects, and you wanted to say how many ways are there of arranging them, then there would be n times n minus 1 times n minus 2 ... times 3 times 2 times 1. Okay, so this comes up so often that we call this n factorial. Okay? I hope most of you have already seen this. Yeah? Okay. Okay. So now, here's a way to actually formally state this rule of counting, the multiplication rule. So what it says is this. Suppose that we want to count the leaves in a tree. And suppose that the tree looks like this. So you have the root. It's a rooted tree. And let's say there's some number of, so there were 4 children of the root. But now, let's say each of the children of the root itself has some number of children. Let's say each of these had two children. Okay, so for this level, everything on this level had 2 children. And now, let's say that for everything at this level, we had some number of children, let's say 3. So everything here, every node here has exactly 3 children. Okay? And now what we're interested in doing is counting the number of leaves. So we want to know how many leaves. Well, one thing we could do is we could just go along and count them. But what the multiplication rule tells us is, look, if you start from the root, there are 4 children. Each of those 4 children has 2 children, so they're going to be 4 times 2 is 8 children down here. And then each of these has 3, so there'll be 8 times 3, which is 24 leaves. So it's just going to be 4 times 2 times 3, which is... Okay, so in general it says, if you have a tree where at each level, every vertex at that level has exactly the same number of children, and you want to know how many leaves there are, then you just multiply the degree of this number of children here times number of children here times number here, right? Okay? Is it clear? Okay. Okay, so that's the multiplication rule. Now, let's talk about a couple of more rules. There's the addition rule. What the addition rule says is, suppose you're counting, what you want to know is, what's the number of elements in the union of 2 sets, A and B? Okay. And suppose A and B are disjoint. It's the empty set. Okay, the intersection is empty. And then A union B is the cardinality of A plus the cardinality of B. Okay? So, for example, suppose you roll 3 dice. And you want to know what's the probability, what's the number of ways. You want to know what's the number of ways of outcomes such that the 3 numbers that show up, okay, at least 2 are the same. So you see at most 2 numbers, such that see at most 2 distinct numbers. Okay, so now we can write this down as a union of 2 sets. So we'll have the set A be the set of all those outcomes such that you see only one number, only one distinct number. And B be the set of outcomes such that you see 2 distinct numbers. You see exactly 2. Okay? And so, what's the cardinality? So, A and B are disjoint, right? Clearly, in the one case you see only one, the same number, only one number. In the second case you see two numbers. So the cardinality of A is exactly what? Well, you know, the 3 dice can come up either all 1s or all 2s or all 3s, etc. So there are 6 possibilities exactly. Right? And what's the cardinality of B? So in how many ways can you get exactly 2 distinct numbers? Well, so let's see. You know, here's an example of such a configuration. It might look like, okay, so you have these 2 are the same and this is different, right? So in order to specify such a configuration, we have to make certain choices, right? We can choose which of these is different. How many ways are there of choosing that? So we can choose. It's either the middle one or the left one or the right one, which is a different one of the 3, right? Because 2 are the same, 1 is different. So we can choose which is different. And then And then we want to choose what are the outcomes. So we have to choose the outcome of, say, the different one. And how many ways are there of choosing the outcome of the different one? Right? So there are 6 ways of choosing what this dice shows. Right? And then you have to choose the outcome of this one. But how many ways are there of choosing that outcome? Right? There are 5. Right? Because no matter what you chose for this one, you have to choose a different one. But no matter what you chose, there are exactly 5 ways of choosing this different thing. So now you have 5. And it's a different 5 depending upon what you chose here, but it's going to be 5 nonetheless. So the total number is 3 times 6 times 5. Okay? And so the addition rule tells us the total number is this plus this. Right? So A union B, cardinality is 6 plus 6, 3 times 6 times 5. Yeah? Okay. Now let's talk about one more rule, which is the subtraction rule. What this says is, suppose that A is a subset of B, and then the cardinality of B minus A is equal to cardinality of B minus cardinality of A. Okay, so let's look at the picture. This is B, this is A. Right? B minus A in this case is the shaded area. Right? And it's telling us the number of elements in the shaded area is the number of elements in the big set minus the number of elements in the small set. Okay? So here's another way of solving this problem. So we want to know, what's the number of outcomes such that you see at most 2 distinct numbers? Well, it's let B be equal to all outcomes, and A be all those outcomes in which you do not see at most 2 distinct numbers. So if you don't see at most 2 distinct numbers, you must see with 3 distinct numbers. Right? And so if you want to know how many outcomes are there with at most 2 distinct numbers, well, it's the set B minus A. Right? B is the set of all possible outcomes when you roll 3 dice. A is the set of all outcomes where you have all 3 numbers are distinct. Right? And so if you take B minus A, you get all those outcomes where you get not everything is distinct, meaning at least 2 are the same. So there are at most 2 distinct outcomes. So what's the cardinality of B? All possible outcomes when you roll 3 dice. 6 times 6 times 6. What's the cardinality of A? All outcomes where the 3 dice show different values. Yeah, it's 6 outcomes for the first one. The second one has to be different from the first one. So no matter what the first one is, you have 5 possibilities for the second one. So 6 times 5, and no matter what these 2 were, you have exactly 4 outcomes for the third one. So 6 times 5 times 4. Okay? So the cardinality of what we're looking for is 6 times 6 times 6 minus 6 times 5 times 4. Okay? Now, of course, because we counted the same quantity, what we've shown is 6 times 6 times 6 minus 6 times 5 times 4 is equal to 6 plus 3 times 6 times 5. Right? These must be the same. Okay? And hopefully they are. Okay? Okay, any questions? Yes. How did we get that the cardinality of A is 6 times 5 times 4? So remember what A is. It says, what are all possible outcomes? A is the set of all possible outcomes where all the 3 different dice have different faces showing. Okay, so how many ways are there of doing that? Well, your first die can show any face at all. There are 6 possibilities. The second one cannot be the same as the first. Right? So whatever the first one was, the second one can't be that one, but it can be any of the other 5 faces. So there are 5 possibilities no matter what this one was. And similarly for this one, there are 4 possibilities no matter what the first 2 were. So I'm using the multiplication rule there. Yeah? Okay. Yes? Why do they have to be the same? Because in both cases, we were counting what's the number of outcomes in which we see at most 2 distinct numbers. Right? So you look at the 3 faces that are showing, and you see only 2 distinct numbers, like here. Right? So 2 of them are the same. At least 2 of them are the same. Right? Okay, so we counted this twice in a different way. Once we said, well, this number of outcomes, there are 2 ways we can achieve it. One, all three faces are the same. Right? How many ways are there of achieving that? That's exactly 6. The other possibility is exactly 2 are the same. And we said this is the number. And so we add the 2 together and we said that's this number. Right? The other way we computed this number is by saying, in order to see at most 2 distinct numbers, okay, that's like saying, okay, that's like this set here, the shaded area, where B is all possible outcomes, no matter whether they are the same or different. And A is, everything which is not here, which is where all 3 are different. Okay? So we are counting the same value in 2 different ways. So we must get the same answer. Yeah? Okay. Any more questions? Okay, so, so since we have a multiplication rule, an addition rule, and a subtraction rule, you would imagine that there must be a division rule. Right? And so we will do a division rule, but let's take a 1-minute break. Okay. So let's build our way up to the division rule. So let's go back and look at this example we had about cards, except now, let's say that you're playing poker, and you're being dealt 5 cards. Okay, so how many ways are there of being dealt those 5 cards? Well, so the answer to this is crucially dependent on, well, of course, if you're playing poker, you're gambling, right? You can't be playing poker without betting. So the answer to how many ways there are of dealing these 5 cards is crucially depending upon, it depends crucially on how you do the betting, right? Because let's say that you do the betting after every card is dealt out to you. Well, then it matters a lot in which order the cards are dealt to you, right? Because maybe if if the first 2 cards were 2 and an ace, maybe it matters a lot which order you saw them in. If you saw a 2 first, maybe you wouldn't have bet on it. But if you saw the ace first, you might get excited and start betting on it, and then you can't stop betting because somebody else bet, and so on. It's all a disaster after that. But okay, so if you're counting, it depends upon which game we are playing. So let's say we are playing the game where we bet after every card. So it matters to us greatly which order the cards are being dealt in. Okay, so now, how many possible different hands are there? Okay, so let's assume that the order matters. Okay, and now we want to know how many different ways can you be dealt these five cards? Well, the answer is you just apply this multiplication rule, right? Because you have 5 cards you want to fill in. You have exactly 52 ways of being dealt the first card. And now, no matter what you've been dealt, there are exactly 51 ways of dealing the second card. No matter what that is, there are exactly 50 ways, and so on. And so the total number of ways of being dealt these 5 cards is this times this times this times this times this. Right? It's some large number. Okay? So in general, if your deck had n cards, and you wanted a k card hand, and we are assuming that the order matters. Okay. Well, then, the number of ways of being dealt this is, well, there's n ways of being dealt the first card, times n minus 1, times so on, times n minus k plus 1. Right? Because it goes from n minus k plus 1 to n minus k plus k. Right? So there are exactly k of them. Right? So you multiply all these out, and that's the number of ways. Now, there's another way we can write this down. We can write this down as just multiply both the numerator and denominator by, so you just say n times n minus 1 times so on, n minus k plus 1. And now you just continue this all the way down, right? So times n minus k times n minus k minus 1 and so on. So you multiply it by n minus k factorial. And you multiply the denominator by n minus k factorial. And see out here in the numerator, what we've done is we've completed n factorial. Right? Because we just continued. We said this goes down to n minus k plus 1, and then we went n minus k minus 1, and so on, down to 1. So this is just n factorial divided by n minus k factorial. Okay? So this was a number of ways of doing this when the order mattered to us. Okay. But now, suppose we want to do the same count, except we want it in the case where the order did not matter. Okay, so now we want to do the same thing. We have n card deck. We want a k card hand, and the order does not matter. Okay, so we are being dealt the 5 cards, but we are not going to do any intermediate betting. You're only going to bet after you get all 5 cards. So it doesn't matter to you in which order they arrived, right? All you care about is what set of 5 cards you got, in any order. Okay? So now, how do we count that? Okay? And this is where the second rule of counting comes up. Okay? So what the second rule says, and it's a very clever, the second rule of counting is extremely clever. It's sort of the, this division rule. So this. Okay, it's an extremely clever rule. So what it says is, let's take the. Okay, so let me say it in 2 different ways, and so let's say it in 2 different ways. So the first way we'll say it is, let's think of creating a bin for each possible hand. Okay, so we create a bin for each possible hand. So each bin will be labeled with a set. So this might be the set where you got the ace of hearts, the 2 of clubs. Maybe it was a 3-card hand just because I'm getting tired, and the 4 of diamonds. Okay. All right? So that's what this bin corresponds to. Then this bin corresponds to another hand. Maybe 3 of clubs, 2 of diamonds, and 5 of spades. Okay? But now, what do we put inside the bin? Well, inside the bin we put all possible. So here the order doesn't matter. So the bin says, the number of bins is what we are trying to count. Okay? So if we were trying to count the number of, if K was 3, the 3-card hands, then we are trying to count how many different bins are there, where every bin is labeled with a different possible hand. So what we want to do is we want to count the number of bins. Right? It's exactly the number of 3-card hands as a set. Now, what do we put inside the bin? Well, inside the bin, we put all possible ways of ordering these. Okay? So given that we got this hand, there are many ways in which we could have achieved it. Maybe there was one where I first got the ace, and then the 2, and then the 4. Right? But there was another way I could have achieved it. Maybe I got the 2 first, and then the ace, and then the 4. Or maybe I got the 4 first, and then the ace, and then the 2, etc. Right? So you write all possible such sequences in which you could have gotten it. Okay? So for each of these hands, you write inside the bin. You put in every possible way it could have been achieved. Every possible order in which it could have been achieved. So now, if you look at the contents of all these bins together, what do you get? Yeah, it's every possible order, every possible K-card hand where the order does matter, right? So the contents of all bins equal to, well, it's, if you look at, this is all K card hands where order matters. So we know exactly how many such there are, right? So we know how many things there are in all the bins put together. It's exactly all k-card hands where the order matters. It was n factorial divided by n minus k factorial. Is this clear? But now, how many things do we have in each bin? Well, in each bin, we are saying there are many different orders in which I could have gotten exactly these k cards. How many different ways are there? Well, it's all different ways in which you can arrange these k cards. Well, how many is that? It's k factorial. Again, multiplication rule, right? So number of elements per bin is exactly k factorial. Okay? So now, isn't this amazing? I mean, we want to count the number of bins, right? That's hard. So instead, what did we do? We placed inside each bin all possible ways of ordering these hands. This hand, right? And then we said, well, the number of things we placed inside each bin is exactly k factorial. But lo and behold, the number of all things we have placed in all the bins, that's something we know how to count. It's exactly n factorial over n minus k factorial. It's all possible k-card hands in every possible order. Right? So the order matters. So now, if we want to know how many bins there are, we just divide one by the other. Right? Because we got k factorial such ordered hands inside each bin. And we got this many total elements inside all the bins. So the number of bins, therefore, the number of bins is equal to this number divided by that number. Right? It's n factorial divided by n minus k factorial times k factorial. Okay? Now this shows up so many times that there's a special notation for this. It's denoted like this. We place n on top of k without any lines and then inside these brackets. And it's called n choose k. Okay? Okay, so let me say this again. I'm sure many of you have already seen this, but let's make sure we understand. So we have a set S of n elements, 1, 2 through n. Okay, so there are n elements in S. And now we want to choose a subset. Okay, so we want to choose a subset T, subset of S, such that the cardinality of T is K. How many ways are there of choosing this subset? Okay? So number of ways of choosing, or number of such subsets. Of these k element subsets is equal to n choose k. Okay? Which is n factorial over n minus k, whole thing factorial, times k factorial. Okay? By the way, one thing that you should realize is these factorials are very large, right? N factorial is a very large number for even moderate values of n, right? It's like the thing we saw with coin flipping, right? For n equal to 300, this is a huge number. Actually, factorial for n equal to 50, 52 is already a huge number. And this is what makes playing cards interesting. It's because there are so many different combinations, right? And it's also what makes probability interesting on these objects. Okay, now let's go back here and look at this calculation again, just to make sure that because the division rule is a little bit subtle. Let's look at it again, and let's look at it in the context of this calculation. So we said, look, we already saw how many ways there are of ordering your 52 cards. But then we said, suppose instead we only want a 5-card hand. We are playing poker, and the order matters to us. How many ways are there of doing that? And we said, okay, if you have an n-card deck, k card hand, the number of ways is n times n minus 1 to n minus k plus 1. Okay, and then we did this arithmetic trick, where we multiplied the numerator and denominator by n minus k factorial to get n factorial over n minus k factorial. Now, there's another way you could think about this as sort of a trivial use of the division rule. So instead of doing this arithmetic trick, you could just think of it as a division rule, an application of the division rule. So what do? You go ahead and say, well, I want to figure out how many ways there are of dealing a k-card hand where the order matters to me. So let me go ahead and think of it like this. So I'm going to have a bin corresponding to each k-card hand, where the order matters, right? Okay, so I have the first element, second element, third element, fourth element, fifth element. So that's what labels this bin. So sorry, let's there has to be a better way of doing it, right? So let's say that this is the 5 of hearts, the 2 of clubs, 3 of spades, 7 of hearts, 8 of diamonds. Okay, so these were the first five cards I got. So that's what the label of this bin is. Okay, now what are we going to put inside this bin? So what should we put inside this bin? Well, all possible ways of continuing beyond this and distributing all the 52 cards, right? So what we should do is put all possible ways of continuing the sequence and distributing all n cards, right? So I just go ahead and put all possible n tuples, where the first 5 are 5 of hearts, etc., up to 8 of diamonds, right? Right. So I'll have the ordering of all possible 52 cards, where the first 5 look like this. Okay. So now, how many? Each bin has how many elements in it? Right. So there were, this was k out of a total number of cards, which was n. So there were n cards total. And we said the first k were these. And then what we put inside the bin was every possible way of arranging the rest. Right? So how many things do we have inside the bin? Well, how many ways are there of arranging the rest? Well, there are n minus k of those rest. So there's n minus k factorial ways of arranging the rest. Okay? But now, what's the content of all the bins together? Well, the contents of all the bins together is every possible way of starting and then continuing the sequence. So the contents of all the bins together is all possible n factorial ways of arranging those n cards. Right? So all bins together contain n factorial different sequences. Each bin contains n minus k factorial. Therefore, number of bins equal to n factorial divided by n minus k factorial. Okay? So, again, this simple thing we did, which was multiply and divide by n minus k factorial, we could either look at it as multiplying and dividing or doing this bin argument. Okay? Okay, is it clear? Any questions about this argument? Yeah. Okay, what's the principle again? Okay, so let's look at what the division rule says. So let's say we have a set A. A is a set of all ordered outcomes. Okay? So, for example, up there, what we were doing was we were saying, A was a set of all possible ways of dealing a K-card hand where the order matters to us. So this is all possible such hands. And then out of those we said, okay, now let's look at all those sequences which correspond to, which are just reorderings of the same cards. Okay? And so we said, well, here's one, here's another, here's another, here's another, and so on. Right? So if you can say A equal to is the union I equal to 1 to L of B sub I. Right? So suppose this is B1, B2, up to B sub L. Okay? So now, suppose we want to count the number of such sets. So we want to know what's L. Okay? That's what we really want to know. How many such sets are there that we have partitioned the set A into? So we are writing A as the union, disjoint union of the B sub i's. Okay, so where B sub I intersect B sub j is the empty set. Okay, so we have written it as B1 union B2 union B3 union B sub L. Okay, and suppose we know how to count the number of elements in A. Okay, so let's say this number is capital N, and suppose the cardinality of B sub I equal to M for all I. Okay? So then we are claiming L must be equal to N divided by M. Right? If all these sets have equal number of elements in them, okay, and each of them has exactly M elements, and suppose we can count the cardinality inside the bigger set, then we can also say how many of these smaller sets there are. Okay? Sometimes the way this is explained, the division rule is explained, is like this, Suppose that you're trying to count the number of sheep on a field. Okay, and it's very hard to count, it's very hard to count the number of sheep because they're moving around. Then what you can do instead is count the number of feet, number of legs, and divide by 4. Okay, so that's what we are doing here. Okay. Now, okay, it sounds like a ridiculous idea, except that it seems to work here. Okay. Okay, is it clear? Okay. Okay, so let's do a few examples, so we at least know what we are talking about. Okay, so let's do poker hands. Okay, so how many ways are there of dealing a flush? Okay, so a flush, remember, is when you get dealt 5 cards all of the same suit. Right? Okay. And again, so here I'm going to assume order does not matter. Okay, so out of the 52 cards, we are being dealt 5 cards, and we want to know how many ways are there of being dealt 5 cards which are all of the same suit. Okay. Well, so how would we count it? We'd use the multiplication rule and say, well, when you're being dealt a flush, it's either hearts or spades or diamonds or clubs. So there are 4 different ways of being dealt a flush. And then whichever one it is, whichever one you chose, so you chose clubs, so now of the 13 clubs, you've got to be dealt 5 of those cards. So you want to choose 5 out of those 13 cards. So multiplication rule, so we did a multiplication rule here, and then we said we want 5 cards out of the remaining 13. Right? Straight. So straight says you have a sequence, right? So you have a sequence like 3, 4, 5, 6, 7 of any suit that you want, right? The suits can be different for all the different cards. So you have 5 cards which are in a row. Okay, so the smallest such, so ace can either be low or high. So the sequence, the cards are numbered like this, and the largest straight starts with a 9. Because if you start with 9, then 9, 10, Jack, Queen. No. Well, it starts with a 10, doesn't it? 10, Jack, Queen, King, Ace. Right? That's the largest one you can have, because Ace can be both high and low. Okay? And so in order to choose a straight, how many ways are there of doing it? Well, so you may as well, okay, so let's do it this way. So we are trying to decide how many sets of 5 cards are there which correspond to a straight, right? Okay. So now you've seen this thing that people do when they're given their hand of cards. They'll actually go ahead and reorder them and sort them in some order. Okay? And that doesn't change the fact that they have exactly that same hand of cards. So what we could do is, once we are given the cards, we could sort them, the 5 cards, we could sort them. And now if it's a straight, it starts from somewhere. It has some smallest card, and then it's the 5 going up in this order, right? So the smallest one is either an ace or a 2, and so on up to a 10. Because if the smallest one is larger than that, we definitely don't have a straight. Right? Okay, so there are 10 possibilities for the smallest card. And then once you've chosen the smallest card, you know exactly what the other cards are. Right? You know exactly what they are in denomination, but you don't know what they are in terms of suit. So how many suits are there for those cards? Times 4 raised to the power of what? 5, right? Because we don't know the suits of, all the 5 cards can have their own suits, right? So so we'll get 4 to the 5. So that's the number of straights. How about full house? So a full house is when you have 2 of one denomination and 3 of another, right? So you might have a full house. You might have king, king, 3, 3, 3, right? So you have your 5 cards look like that. Okay, so we've got to pick this denomination. So how many ways are there of doing that? 13. And then we pick the 2 cards themselves. So how many ways are there of doing that? So we have to pick the. So what we are trying to do is we've picked the fact that it's a king, but now we want to know what suit are they. Okay, so we are picking 2 kings. How many ways are there of doing that? There are 4, choose 2. Right? And then, no matter how we've picked these, so once we've done this, how many ways are there of picking these cards? 12, right? So there are 12 ways of picking the denomination. So times 12. Because we already picked the king, so these cannot be kings, right? So they can be any of the other 12. Times, now we've got to pick the suits of these. Right? So we know we picked 3s, but how many ways are there of picking 3 3s from the deck? 4, choose 3. Okay? 2 pairs. Okay, so 2 pairs is something like this, So suppose you have king, king, 3, 3, 8, right? So you have 1 pair, a second pair, and then this card has to be different from these 2, right? This denomination has to be different from these 2. Because if it was one of these 2, you'd be in the full house situation, right? So for it to be 2 pairs, it's got to be 3 different denominations. Okay? Okay, so now, should we be saying, well, there are 13 ways of picking this one times 4, choose 2, times 12 ways of picking this one times 4, choose 2, times 11 ways of picking this one times 4. Does that look correct to you? Right, there are 13 ways of picking what this first one is, and then you've got to pick what the suit is. So you have to pick off the 4 cards, 4 kings. You have to pick 4, choose 2. You have to pick 2. Then there are 13 ways of picking the second one. Right? Sorry, there are 12 ways because you already picked the king. Times 4, choose 2. And then there are 11 ways of picking. Now you've picked the king and 3, so there are only 11 possible denominations left. And once you pick that, you will still have to pick the suit. So does this look right? It's wrong. Yeah, why? That's a good question. So why should it be wrong? I'm sorry? Yeah. Yeah, but it doesn't matter. 13 times 12 times 11 is the same as 11 times 12 times 13, right? So that's okay. So what else could be wrong with this? Yeah. This shouldn't be 4 suits. This should be 2. Why is that? Yeah, Okay, so so far we are okay. So, by the way, it's not. I mean, the suits don't have to be different from each other. There's one thing we haven't taken care of here, which is we haven't said, by the way, that this is not a flush. Right? So it could be that all of these could be the same suit, but let's not even worry about that. Let's say that it's two pairs and we don't care if it's a flush. If it were a flush, we'd have to remove one of these possibilities, but that's okay. Yeah? Yeah. So you see, the fact that I said, well, I first picked these kings, and then I picked the three, right? Who told us that, how do you distinguish between these two? Right? It's two pairs, right? This is a pair, and that's a pair, right? We just can't distinguish, who told us whether we are picking the kings first or the threes first? Right? We can pick them in any order that we want. Right? Does everyone get that? So the number of ways of picking whether it's king and 3 are the two pairs is not 13 times 12, it's 13 times 12 divided by 2. Right? Because I could pick king, 3, 3, or I could pick 3, 3, king, and 8. And these two are the same, they are the same hand, whereas I'm counting them as two different hands here. Right? Because I said there are 13 possibilities for what you pick here, times 12 possibilities for what you pick here. But they aren't, right? They are 13 times 12 divided by 2. And how would you get 13 times 12 divided by 2? So you could either say this divided by 2, or you could say, well, I want two pairs, right? So I have to pick which two denominations I have out of the 13 denominations. So I choose 13, choose 2. Now I've picked the two denominations. For each of those denominations, I have to pick 2 cards. So I choose 4, choose 2, whole squared. Right, now I've picked the 2 cards for each of those denominations. And then I pick this last one, 11. How do I know I can't move this forward? Wouldn't that be a different, am I not counting that separately? I mean, am I not making a mistake there? Shouldn't I divide this all by 2 again? No, right? Because if you look at, if I were to write 8, 3, 3, king, you'd say, look, give me a break. I can identify 8 as the loner here, regardless of whether you put it in front or in the back, right? But in terms of the 2 3s and the 2 kings, who's to tell? How do you tell which one is which? I mean, they're both a pair, right? Whereas this 8 is by itself. It's different from the 3s and the kings, right? So okay? So I can multiply by 11 times 4 because there are 4 possibilities for the suit that this 8 is. Okay, and that's the total number of possibilities. Okay?